So good morning, everybody. It's a pleasure for me to introduce Elena Zaninoni. She studied in Padua, and then she moved to Milan, where she has her PhD. And she ended the PhD in April this year. Okay. And today she will talk about gamma ray burst and direct X-ray and optical afterglow.
Thank you. And so, as Stefano said before, I study for my PhD gamma ray burst, and particularly I focus on their X-ray and optical afterglow. I work in Milan with the group of Professor Kincarini, and I collaborate with Maria Grazia Bernardini and Raffaella Margutti and Sam Oates and some people of the SWIFT team. Briefly, I will introduce you something about gamma ray bursts in general, and then I will focus on the two main projects that are the X-ray light curve and the optical light curve. Okay, gamma ray bursts are sudden and intense flashes of gamma ray radiation, and they are very luminous and energetic. In fact, they have a isotropic luminosity that is of order of 10 to 54 ergs per second. Historically, they are divided into two groups that are long and short gamma ray bursts, in particular considering the duration in the gamma ray emission. In fact, as I shown here, the T90, that is a characteristic in time, and we can show the short gamma ray burst here and the long gamma ray burst here. Moreover, the difference between these two groups is the difference order ratio. That is, we have this blue line are long gamma ray bursts that are softer than a short gamma ray burst, that is this red line. Moreover, we can also detect the host galaxies of gamma ray bursts, and so we connected the long gamma ray bursts to late type host galaxies. Instead, short gamma ray bursts are shown that explode in every kind of galaxies. And for this reason, so long gamma ray bursts are associated to the death of massive stars, and so they are connected to supernovae explosions. And the short gamma ray bursts instead come from the merging of a compact object as a neutron star and black holes. They are also different for the energetic, because long gamma ray bursts are more energetic in the gamma rays than short gamma ray bursts. Here I show the Amati relation. It is the relation between the peak energy, that is, this is the spectrum, this is the peak energy, and the isotropic gamma ray energy. And so we can see that this is the relation for long gamma ray bursts. In fact, this correlation is follow only for long gamma ray bursts, and this red part is our short gamma ray bursts that stay in another part of this plane. Okay, when we observe gamma ray bursts, we can observe in every kind of wavelength. In fact, we observe in gamma ray, for example, for gamma ray bursts 0810, we can observe this is the light curve of Fermi GBM instrument. Then this is the SWIFT BAT, that is the gamma ray instrument on board of the SWIFT satellite. Then we can observe the X-ray light curve, that is this one, blue. Then we have also the optical observation, that are this color light curve, in this case the red and green and the blue one. And sometimes we can observe also radio in the radio band. In this case, the points are here. In particular, because I focus my project on X-ray light curve, where I want to show you that the 30% of X-ray light curve has a canonical shape. That is, they start with a steep decay, then we have a plateau phase, and then a normal decay. And sometimes that is more or less 30% of the cases, we observe also flares superimposed to the continuous part of the light curve. Then, instead, for the optical lecture, we have a more complicated feature. In fact, we can observe bumps, we can observe some initial rise, and then some initial plateaus, and we can also observe supernova bumps or late rebrightening. To explain all these characteristics, many models have been proposed. For example, this is the standard model, that is the internal and external shock model, in which we have a massive star that collapses for the long gamma ray bars when we form a long gamma ray bars instead. Or we have the merging of two compact objects, that is the scenario for short gamma ray bars. And so we form a central engine and then a jet. And when this outflow catch up in the external medium. When we have, firstly, we have in some internal shock, that is the fast shell catch up the slow shell, and so we have internal shock, and we have the prompt emission, that is we have this part of the emission, that is the gamma ray emission. Then the jet propagates into the external medium, and then we have the afterglow. And the afterglow, that it means that we observe the X-ray, the visible, and the radio emission. And this is, for example, in this part of this light curve. And we have also some models that are concentrated on the type of the progenitor. For example, for long gamma ray bars, we have the model of the hyper-accretion onto a black hole, and it is in particular the Kumar model. In this case, the different part of the light curve depend on the part of the shell that accretes onto the black hole. And finally, there is also sometimes we know that the progenitor could be a magnet, that is a fast rotating egg-magnetized neutron star, and this model in particular can reproduce very well a relation found by Zaninoni. That is a relation between the luminosity of the end of the plateau in the X-ray light curve and the end plateau time. In fact, we made some simulation to show that this model can explain very well this correlation. The gray points are the simulation that take into account different period and different magnetic field, and to reproduce this characteristic, that is the end plateau time and the luminosity. And we can see that the observation are the color points. And as shown in this figure, we can see that the model can explain very well this correlation. Okay, after this introduction, I wanted to show you some highlights about the main project about the X-ray light curve that is based on these articles. Okay. We started considering all the gamma ray bars observed by SWIFT satellite between 2004 and to the end of 2010. Then, so we have more than 600 GRBs. Then we use only the GRBs that have time resolved spectra, and so we can to obtain a flux and luminosity light curve. So we have calibrated in flux and luminosity. In this way, we obtain a sample of 400 GRBs. The importance of this sample is that we have a big sample of GRBs with redshift, and so we can we can compare, we can study the rest frame properties of GRBs. Then we have also a small sample of short GRBs that is important because in this way we can compare if there are some similarities or differences between short and long GRBs. In particular, we fit all the X-ray light curve, not considering the X-ray flares, and we collect 44 parameters from this light curve fitting for the energetic of the X-ray emission, and also we collect this parameter from literature to put also some characteristic of the prompt emission. In this way, what we did is to see the parameter distribution and also to find out and we tested also two parameter correlation. Okay, in particular, I write this automatic software that eliminates all the flares and so we can have only the continuum part, the fit only of the continuum part of the light curve, and we classify this light curve considering firstly we consider the number of breaks in the number of breaks in the light curve, and then in fact we have a type 0, 1, 2, and 3, and the type 2 A is the canonical shape, and then we consider also, we classify if there are or not flares, and if we observe before 300 seconds after the trigger, and we have observation until 10 to 4 or 10 to 5 seconds after the trigger. In this case, for example, we have GRB 060312 that is classified as type 2 because as a 2 break, complete as with flare. I want to underline that the red points are the points that are automatically eliminated by the program. From all the, we fitted the light curve, we collected the data, we tested all the two parameter correlation, but but for us it was more interested to find out some correlation more complicated, that is that consider more than two parameters. In fact, using the principal component analysis, we find in this sample of 44 parameters, we find a correlation between three parameters. But in particular, we found two parameters that are related to the prompt emission, that is the peak energy, and the isotropic gamma ray energy. And the third one is the parameter for the afterglow, that is the isotropic X-ray energy. This is the three parameter correlation, and the blue is the dashed line, and we can see that this correlation is important because it is followed by long gamma ray bars. We can find also subluminous gamma ray bars that are gamma ray bars that has less X-ray luminosity. Short gamma ray bars, and for example there is also 1178A that is a gamma ray bars that it wasn't in our sample, but it can fit well in this relation. Also outliers that are GRBs that are outliers of previous correlation. And also peculiar GRBs as 11, 12, 09, that is a very long-lasting GRBs. So the particular thing of this correlation is that it is a three-parameter correlation and fit well for every kind of GRBs, and not only for, as we showed before, only for long or short GRBs. And moreover, we can see that here we have two groups that are gamma ray bars that have a lower X-ray energy, that is short, and subluminous GRBs that have X-ray energy lower than 10 to 51 erg. and the long GRBs that stay in the part with high X-ray energy. So this is what we find about thanks to the data, but what is the physical parameter that can drive this correlation? And we rewrite this correlation taking into account the efficiency of the GRB to convert the initial gamma ray energy, what we see in the gamma rays, into the afterglow and in particular in the X-ray energy. In this case, we can see that we have two groups. We have subluminous gamma ray bars that are less efficient. Instead, the long and the short gamma ray bars stay in the same part of the plane, and so they show the same efficiency. From the works of Ghirlanda and Genius and other papers, we found out that the peak energy can be related to the Lorentz factor of the outflow. And in this case, rewriting our ratio, we can see that the physical parameter that can create this correlation is in fact the Lorentz factor of the outflow. In fact, this was confirmed by some models, by the photospheric model, in particular in the paper of Lazzati and collaborators. So in this case, I show you that a study about X-ray light curve that we study considering with a statistical approach. We have a very large sample of data, and in particular we did this study not considering a model, and so it is model independent. Then, and in particular, we concentrate on in analyzing the prompt and the afterglow properties, and the measure result is the three-parameter correlation. And this is the end of a general project about X-ray light curves. In fact, with this work, we studied the continuum part of the light curves, and before my group studied also the flares characterization. So now we can move on with the optical light curve of GRBs. Okay, these are in general some characteristics of optical light curve that was found in previous work. For example, optical and X-ray light curve are different at early times. We have different initial behaviors with peaks or plateaus. We have X-ray and X-rays light curve that decay faster in general than optical light curves, and so on. In this case, this previous work usually mainly concentrated on data obtained only by a single telescope, and only few papers try to look data from different instruments. In this case, I started considering all the GRBs with redshift that in our previous sample of the Swiss satellite of the X-ray data. And so, starting from these GRBs, I look for all the optical data that are presented in the literature. So, we obtain a sample of 68 GRBs with no redshift, with optical data that are published in referred papers and coming from different instruments. In this talk, I will focus only in three different characteristics, and that is the different light curve shapes, their gas-to-dust ratio, and then the optical and X-ray spectral energy distribution. Considering the shape of the optical light curve, we can show that the X-ray are the color one of the color light curve, instead the gray one are the optical. And we can show that the optical light curve can be as an initial peak that it is depends of the it is the onset of the further shock, and so we have outflow with the same Lorentz factor instead or we have okay, and also okay, there are the two cases with a peak. Then we have an initial, we have also an initial plateau, okay, that is the area that are highlight, and in this case they can be created by, for example, the ejector release, or we have a rejector with a different initial Lorentz factor. Then other characteristic features of this light curve are some late time rebrightening, that is depends on the jet structure, or we have initial big bumps, or we have small bumps during the light curve. Okay, these are all the characteristics of the optical light curve, but it is interesting to notice if there are what happen in the X-ray light curve and in contemporaneous with the optical light curve. That is, we can see that during the step decay, the plateau and the normal decay, that as I showed before for the canonical shape of the X-ray light curve, we can show what happened during the optical light curve. In this case, we show that there are different features in the optical light curve, but we can see that as the time goes by, the complexity of the light curve reduces, and the majority of them decays. This is because, in fact, the X-ray normal decays is only afterglow emission, and it is not, there is no influence by the central engine that can make some different feature of in the light curve. In fact, for example, the X-ray steep decay, we have in the steep decay, the X-ray light curve is influenced by the central engine, and the same can occur in the X-ray plateau because the plateau seems to be the injection and a more energy injection by the central engine. Okay, another feature that is only okay, there are some images about this, that I know that the X-ray flare can occur during the steep decay, or during the plateau, as I showed before. And we show that this could be a link between the flares and the shape of the optical light curve. In fact, we can see that where there is a flare, could be a peak in the optical light curve, or there is the end of a plateau. In fact, the onset of the further shock observed in the optical light curve could be linked to the presence of the X-ray flares. So, the other step was to make the spectral energy distribution considering the optical and X-ray data, and we use the optical extinction law for the Milky Way, Large Magellanic Cloud, and Small Magellanic Cloud, the X-ray extinction law, and for the fixed function we use a single power law or a broken power law, and the statistics said us what model was better in the single case. And we made this SAD considering different time during the emission. And the gray bands correspond to the bands where we made the SAD. And so if we have a single power law, so we obtain only the spectral slope, the hydrogen column density, and the optical extinction. Instead, if we have a broken power law, we have two different slopes for the optical part of the data and for the X-ray, and also the break frequency. So from this SAD, we can study the gas-to-dust ratio of the environment of the gamma ray bars. And in this case, and so from the hydrogen column density and from the extinction of the optical extinction, we found out that the gas-to-dust ratio observed for the gamma ray bars is greater than the values found in literature for the Milky Way, for Milky Way, Large Magellanic Cloud, and Small Magellanic Cloud. In fact, we can see in this plot the stars are the values that we find in literature. Instead, the Gaussian and the histogram are our data. The other thing that we can study with this data are the closure relation. The closure relation are based on the standard model of the 4 gamma ray bars and are based on the synchrotron emission. That is, we have a synchrotron spectrum, and then we can see the relation between the spectral slope and the light curve slope, that is the temporal slope. And so we find out that these relations are followed by only 4% of gamma ray bars only during the protophase and only the 12% during the normal decay. And so we found that no gamma ray bars follow the close relation for all the phases of the light curve. That is what this is important, because our data are inconsistent with this simple model, with this standard model, and so this model can reproduce the observed afterglow emission. Therefore, because the optical and X-ray observation are well fitted with a synchrotron spectrum, therefore we need a more complex hydrodynamic evolution of the outflow to model our observation, or to consider the direct influence of the central engine. Finally, we consider also a broad-based SAD. That is, Chandra and Frey published his paper in 2012, and in which there are some radio data of gamma ray bars. And we found that these gamma ray bars 07, 10, 03, we have the same data at the same time of the data of Chandra and Frey. So we can rebuild the SAD from the radio to the X-rays. We consider the model presented in the papers of Sari and Gano, that is, we consider the synchrotron asynchrotron spectrum, and we use these breaks because in our previous fit of only the optical and X-ray data, we found out that it is this GRB is well fitted by a single power law, and so the Coulomb frequency and all the frequency are before the optical band. So we found out that this GRB, we can reconstruct this SAD, and we found out that this GRB could have a total energy of about 2 for 10 to 52 ergs. Okay. This is to conclude. These are all the things that I studied, presented in the paper, and this paper, even if I didn't list or I presented you only some major characteristic of major result of the article, and in particular, so to make a summary, in particular, we fit so the optical curve that we from the optical curve collected from different instruments, and also we made different optical X-ray SAD. We consider different time to make this SAD. In particular, we obtain also a spectral energy distribution for a GRB with the data also in the radio band. Then we studied the distribution of all the parameters that we computed from the SAD, and so we studied the medium and the spectrum of GRBs. And for example, we found out that there is a slight softening here of the optical X-ray spectrum with the time, and there is a difference that the gas to dry ratio of GRBs are higher than the values calculated in the literature for Milky Way, Large Magellanic Cloud, and Small Magellanic Cloud. Moreover, we made we studied the flux the optical flux and the X-ray flux, and we show that the optical flux in our band is 2 order greater than 2 magnitude greater than X-rays, and so on. We tested also some correlation, and in particular we find out that the forward shock model, that is the standard model that is based on the synchrotron emission, is cannot explain or feature that are presented in the optical air and X-ray light curve, and so the and moreover, as I presented before, the 3-parameter correlation that consider only the X-ray emission, okay, and the X-ray emission is at the afterglow, and so I tested also say if in the afterglow we consider the optical energy, if this correlation can change or this contribution can be great, and in this case not. I calculated that the contribution is very low because it is less than the 10% of the total energy that is emitted. So concluding, we have studies a correlation between 3 parameters that involves the prompt emission property, that is the peak energy, the gamma ray energy, and the afterglow emission, that is the X-ray emission. And this is particular because it's followed by long, short, and peculiar GRBs. Moreover, we study, so we can ask if short and long gamma ray bars have similar properties or not, but we have not now an answer to this question. So we must search for a new model that explain well this relation. We know that optical X-ray emission properties are different, and only in 2 cases there are some relation between them, and seems that the synchrotron model, that is the standard model that is the base of the fundamental models, can fit well the spectral properties, but we need a more complete model to explain well the evolution of the fireball and so the observation about GRBs. And so I think that we need a catalog with timers of optical curve to study in more detail the characteristics of these objects, and in particular that we need data that are at a very early time after the trigger. So we need multi-wavelength observation that are useful, as I showed before in the study of the SED, and also early time observation, and so to trace the evolution of, in particular, of a GRB. Okay, thank you.
Yeah, thank you very much for this nice talk. We have time for questions.
Yeah, so when you were fitting the light curves,
yes,
how could you distinguish between a break and a flare that was kind of just a little bump?
Okay, we decided before the fit function, okay, that could be used in this case, and every time the program eliminated 1 point that is 1 sigma more than the continuum, and so in this case with the iteration we can eliminate our flares and we see the breaks, okay, or we can try different mode.
So was there anything different about the spectra of the flares compared to the parts of the continuum without flaring or anything like that?
Okay, it is different because the flares are very harder than the continuum parts.
The flares are harder.
Okay, are harder.
Okay.
And so
okay.
you can consider only the continuum parts of the.
Okay.
You mentioned the parameters efficiency. Could you tell me, for those like me who are not what is the meaning of the efficiency in these sources? Okay,
the efficiency is because we have the first prompt emission that is in the gamma rays, and then we observe also the X-ray emission. Okay, and it is to convert this prompt emission in the afterglow. This means as efficiency, and so it is a sort of kinetic energy that how to dissipate this energy. And so it is Okay, is a conversion when we start with this energy in the prompt emission. We can see, for example, the internal shock, then the outflow move on in the external shock, and we observe other energy. It is a conversion. Okay, more efficient gamma ray bars. It is gamma ray bars that have high energy also in the X-ray, in the afterglow instead, and not only in the prompt emission. That is, it is a conversion of energy in the second part of the emission. Yes, it is a release. Yes. Is converted, yes, is released, and so we have higher higher Lorentz factor for the outflow. Okay. Okay, yes.
That you may have, or you can have a result, low efficiency in your case.
Okay.
May result in high efficiency in, for instance, star formation.
Okay.
Because, sorry. I understand your
okay.
I don't know if I understand, but if I understand well, it means that the more the energy you lose, yes, energy, the less that you keep inside the system. And probably the mass is also related with this.
Okay,
right?
yes.
And then if you have a low efficiency in your
okay,
definition, it may result in the fact that you have more energy inside,
okay,
and probably whatever result from the fact of retaining energy, okay, and mass within the system. So okay, this, in the case of massive starbursts,
yes,
you may have that if this is the case and you don't lose energy, mass with outflows or whatever,
okay,
as a result, you have more things to keep working. So to
okay,
produce more stars, to produce massive bulges, to produce whatever. So
okay,
that's why it seems to me that this parameter that you mentioned can be very important also in a more extended ground, for instance, for star
okay,
formation or for black hole production, these sort of things. I don't know.
Okay, I don't know if it is we can put this also star formation and okay, because we related this only on the physics of GRB and then the Large Magellanic or the outflow, but not in this case. But it is interesting to
provided that
yes, to provide.
You know all the database, and I'm sure that all these gamma ray things,
okay,
you have already cataloged. You know where they are. You know what are the properties, whatever, right? And so in some cases, because you have the spectral energy distribution, you know what sort of things are those, and it could be interesting to compare this value efficiency that you have parameterized with this other thing that you get from the principal component analysis. You may try to correlate this value with other parameters related with star formation, with galaxy formation, whatever, because it may be, I don't know, it may be related.
Okay.
I might be wrong about this, but I thought a lot of the interactions with the jet in the afterglow were happening with the wind that the progenitor star had launched rather than the general interstellar medium. Is that right?
Okay. Okay, there are different models. That is, we have a constant density medium in a model, or we can consider also a wind medium. Okay, and these the relation are a little bit different because the wind can interact in a different way, and so also, for example, the closure relation are different if you consider a wind model or not a wind model in this case.
Any more questions?
Do you have this thing that you are discussing now has to do with the fact that these gamma ray bursts can be point-like objects, or they can also be extended things, right? Which is have you already worked on the morphological things. I mean, how do they look? These 68 sources that you have been analyzing, you work with the spectral energy distribution because you have measured it as points, or, I mean, are they extended? What are they points in the sky? What are they? I mean,
what we are it is.
I mean, you have. Sorry, maybe this is very silly. I mean, so you know.
For example, don't know if it is well the question, but it's okay. We have we form. I don't know if it is.
Yes.
Okay, maybe this can.
Okay, so you have all sorts of things.
Okay, we have. It is from a black hole and then a jet, and what we observe an interaction of the jet within the stellar medium, and this. Okay.
Yes, that's I understand, but then you have six. Yes, I mean you have somehow a list of targets in which you know the energy distribution, okay? And you know the position, or the possible position, right? My question is very simple. In those surveys, which now we have many, deep images, deep surveys in different wavelengths, are they all similar? Some are extended things, some are point-like things, some are jet-like things. How do they look like?
The problem is that gamma ray bursts can start and then die.
Okay, but
I don't understand the question.
You know where they were.
Yes, we know where.
Maybe you may have now an empty point because the gamma ray already died.
Yes, you can study.
But you know where it was.
No, we don't know where it was. Only sometimes where we can detect.
You have a big box with uncertainty of where this thing is taking.
Okay, we observe an emission. Because gamma ray burst is very particular because we have a SWIFT that for other telescopes now that can survey all the sky and then detect gamma ray, and so all the other instruments can observe in different wavelengths. I don't know. Okay.
Gamma ray burst happened. You are asked to point the telescope to the
plane. Yes,
right.
Because we know very well the position. Because when explode the gamma ray burst.
So I suppose there will be many who somehow are maybe not identified. Some are identified, but some others you know more or less. I mean, you have a guess of where in the sky these things has happened, right?
Okay.
No.
Right.
I just wondering if you do this sort of cross comparison of the gamma ray bursts, and the possible space in the sky or the area where they happen, or these sort of things about the morphological and spatial distribution of these gamma rays.
The spatial distribution is isotropic of the gamma ray bursts. In fact, it is one of the first things that lead to the consideration that the gamma ray bursts are extragalactic objects for this. In fact. I don't know if I understand well the. No, I don't understand. Okay.
It's not lunchtime yet, so I think it's okay. You mentioned at the beginning that one of the explanations for the plateaus was magnetars, and then unless you went through it really fast at the end, I think I missed whether you came back to that. Could you comment on that a little bit more? What's the current thinking about these magnetar models?
These?
Yeah.
Okay. The magnetar models is for the
So do people believe that that's actually happening in both long and short gamma ray bursts, or the magnetar idea?
Okay, that is there are some models that explain that magnetar will be a progenitor, and there are people.
So a single magnetar is the progenitor, or it's a massive star and then it turns into a magnetar temporarily during the GRB. What's the whole picture?
Yes, it's a single magnetar because this is the picture for long gamma ray bursts and not for short gamma ray bursts.
It wouldn't apply to short gamma ray bursts. Okay. So then if this is going on, then is your relation that includes the long and short ones just a coincidence?
No, I don't understand, sorry.
The three-parameter relationship that included long and short camera bursts.
There is, the three parameter here.
Yeah.
Okay.
Right, so if the magnetar model applies to the long ones but not to the short ones, is this plot here just a coincidence that all the different types of objects fit on the same plot?
Okay, I don't know. We didn't. We didn't know if it is the magnetar model or another model can fit very well this correlation. In fact, the only model that considered this three-parameter correlation was the photospheric model that takes into account the photospheric emission, but is different from other models. And the theoreticians are investigating about this thing also, and they know well if also what kind of model can link together this. Also because, the problem here is that we have long and short gamma ray bursts in the same correlation. And so it is something that is different from the progenitor. It could be something that is after the progenitor.
Okay, if there are no more questions, let's thank Elena again. Have a good day.
Aiuto. Sorry.